Quantum teleportation, how it actually works. Hey there! Today we'll explore one of the most mysterious phenomena in quantum physics, quantum teleportation. And here's a spoiler right away. There will be no stargates or instant space travel. Reality is far more interesting than science fiction. Let's dispel the myths first. Quantum teleportation does not mean instant transmission of matter or energy, moving objects from point A to point B, breaking the speed of light, the ability to teleport like in movies. So what is it then? Quantum teleportation is the transmission of a particle's quantum state over distance, without physically transferring the particle itself. Sounds strange? Let's break it down. For quantum teleportation, we need three things. First, quantum entanglement. This is when two particles become linked so that measuring one instantly affects the state of the other, even if they're on opposite ends of the universe. Einstein called this spooky action at a distance and couldn't believe it, but experiments proved it's real. Second, classical communication channel. Yes, ordinary communication. This could be internet, telephone, radio, anything. Without this, teleportation doesn't work. Third, the particle whose state we want to transmit. Let's call it Alice. Imagine, we have Alice and Bob. Physicists love these names. Alice wants to transmit the quantum state of her particle to Bob. Step 1. Preparation. First, a pair of entangled particles is created. Alice gets one, Bob gets the other. These particles are now linked by quantum entanglement. Step 2. Bell measurement. Alice performs a special measurement called a Bell measurement between her original particle, the one whose state needs to be transmitted, and her half of the entangled pair. This measurement entangles them with each other. Important point, this measurement destroys the original state of Alice's particle. This isn't a bug, but a fundamental feature. You can't simultaneously copy a quantum state and transmit it. This is called the no-cloning theorem. Step 3. Information transmission. Alice's measurement result is 2 classical bits of information. She sends them to Bob through an ordinary communication channel. And here's what's important. This transmission is limited by the speed of light. No magic. Step 4. Reconstruction. Bob receives the information from Alice and applies a specific operation to his particle depending on the received data. And voila! Bob's particle is now in the same quantum state as Alice's original particle was. Notice the paradox. Without transmitting classical information, Bob can't reconstruct the state, even if he has the entangled particle. This means information is not transmitted faster than light. The original state is destroyed at Alice's end. It's truly teleported, not copied. We can't know what was transmitted just by looking at the entangled pair. You might ask, so what? Why all this complexity? Quantum teleportation is the key to quantum computers and networks. It allows quantum information to be transmitted between quantum processors, creating distributed quantum computing. Quantum cryptography. This is the foundation for absolutely secure communication. Any interception attempt will destroy the quantum state and be detected. Quantum repeaters. Special devices are needed to transmit quantum information over long distances, and teleportation is their foundation. This isn't theory. Quantum teleportation has already been achieved. 1997, first successful teleportation of a photon in a laboratory. 2012, teleportation over 143 kilometers between the Canary Islands. 2017, Chinese satellite Mischius conducted teleportation between Earth and orbit at a distance of 1,400 kilometers. 2020's quantum networks actively being built in China, Europe, and the USA. Not just photons have been teleported, but also atoms and even entire ions. Progress is advancing at breakneck speed. Now the bad news for Star Trek fans. To teleport a human, you'd need to precisely measure the quantum state of each of approximately 10 to 28 atoms in the body. Transmit this information. Recreate an exact copy at the other end. The original you would be destroyed in the measurement process. Even if this becomes technically possible someday, which is extremely unlikely, philosophical questions arise. Is it still you? Or is it a copy while the original died? Quantum teleportation is an incredible example of how quantum mechanics challenges our intuition. It shows that information in the quantum world behaves completely differently than in the classical world. It doesn't violate the laws of physics, doesn't exceed the speed of light, but allows us to do things that seemed impossible. And this is real technology that's already working and developing right now. Let's dig deeper into quantum entanglement itself, because this is the heart of the entire process. Imagine two coins. In a classical world, if one lands heads, the second can be anything, heads or tails, independently. But quantum entanglement works differently. Entangled particles are in superposition. They're simultaneously in one state and another until you measure. But here's the magic. When you measure one particle and it chooses a state, the second particle instantly knows about this and chooses the corresponding state. This doesn't mean some signal is transmitted between them. They're just connected, as if they're two sides of one coin, separated in space. Einstein struggled with this idea until the end of his life. He proposed that there must be hidden variables, some information we just don't see that determines the result in advance. But experiments with Bell inequalities in the 1960s, 80s showed Einstein was wrong. Nature really is that strange. Now about the mysterious Bell measurement I mentioned earlier. This isn't just an ordinary measurement like, let's see what's there. This is a special quantum operation that simultaneously measures the properties of two particles and determines how they relate to each other. When Alice performs a Bell measurement between her original particle, let's call it message, her half of the entangled pair, she gets one of four possible results. These results can be encoded with two classical bits, 00, 01, 10, or 11. The beauty is that this measurement entangles the message with her half of the entangled pair. And since her half was already entangled with Bob's particle, a chain is created. Message Alice's particle Bob's particle. As a result, the message state is kind of imprinted on Bob's particle, but in encrypted form. And the two classical bits are the decryption key. The concept of quantum teleportation was developed in 1993 by an international team of physicists, Charles Bennett, Gilles Broussard, Claude Crepeau, Richard Jassa, Asher Perez, and William Wouters. This was pure theoretical insight. They realized that by combining quantum entanglement, which seemed just a strange phenomenon, classical communication, ordinary, boring information, Bell measurements, complex quantum operations, you could do something completely new, transmit a quantum state without physically transferring the particle. This was so revolutionary that many physicists didn't believe it at first. It seemed to violate fundamental principles, but the mathematics was flawless. The first experimental realization came just 4 years later, in 1997, in two independent laboratories in Innsbruck, Austria, and in Rome, Italy. They teleported the state of a photon. Since then, it's become a routine procedure in quantum laboratories worldwide. It sounds simple in theory, but in practice, everything is more complex. Problem 1. Decoherence. Quantum states are incredibly fragile. Any interaction with the environment, a scattered photon, thermal motion, a magnetic field, can destroy quantum information. This is called decoherence. Therefore, experiments are conducted at temperatures close to absolute zero, in vacuum, with careful shielding from external fields, very quickly before the state is destroyed. Problem 2. Creating entanglement. Creating a perfectly entangled pair of particles is difficult. Special sources are needed, and efficiency is often low. Out of 1,000 attempts, you might get several good entangled pairs. Problem 3. Distance. When transmitting photons through fiber optic or through air, they're absorbed and scattered. The farther, the lower the probability of success. This is the main reason satellites are used. There are fewer obstacles in space. Problem 4. Measurement efficiency. Detectors aren't perfect. They might not register a particle or give a false signal. This reduces the accuracy and reliability of teleportation. To solve the distance problem, the concept of quantum repeaters was invented. In classical networks, when a signal weakens, we simply amplify it. But with quantum states, that won't work. They can't be copied or amplified without destruction. A quantum repeater works like this. Create entanglement between point A and the repeater. Create entanglement between the repeater and point B. Using a special entanglement swapping procedure, create entanglement directly between A and B. It's like teleportation of entanglement. The repeater becomes an intermediary that creates a connection between remote points. With a chain of such repeaters, you can create a quantum network over any distance. China is already building such a network thousands of kilometers long, connecting major cities. Where is all this leading? To a quantum internet, a network where nodes are connected by quantum entanglement. In such an internet, absolute security. Any attempt to intercept information will be instantly detected because measurement destroys the quantum state. This is an encryption that can be broken with a powerful computer. It's physically impossible to break without detection. Distributed quantum computing. Quantum computers in different cities or countries will be able to work as a single system, exchanging quantum states through teleportation. Quantum sensors. A network of ultra-sensitive quantum sensors linked by entanglement can detect gravitational waves, magnetic anomalies, or even earthquakes with unprecedented accuracy. Time synchronization. Quantum entanglement can provide ultra-precise clock synchronization worldwide, which is critical for GPS, financial transactions, and scientific experiments. The first prototypes of a quantum internet already exist. In 2022, researchers created a 3-node quantum network in the Netherlands, where nodes exchanged entangled states. Let's look at the most impressive achievements in quantum teleportation. 2004, atom-to-atom teleportation inside a trap. First time they teleported state between matter particles, not just photons. 2009, teleportation between atoms at a distance of 1 meter. Sounds modest, but it was a breakthrough. Proved it's possible to teleport between separate atoms in different places. 2015, reliable teleportation with efficiency above 98%. Previously, only a small fraction of attempts were successful. Now the process became almost reliable. 2016, Calgary, Canada. Teleportation through urban fiber optic network, 6.2 kilometers long. This was real infrastructure, not a laboratory setup. 2017, Mishia's satellite teleported photons from orbit to ground stations in Tibet at distances up to 1,400 kilometers. Absolute distance record. 2019, teleportation of a qubit, 3-level quantum system instead of regular qubit. Showed the method works not only for the simplest systems. 2022, teleportation through 44 kilometers of urban fiber optic between 2 laboratories with quantum computers. Step toward real quantum internet. 2024, demonstrated teleportation maintaining high accuracy even at temperatures above liquid nitrogen temperature. This significantly simplifies practical application. Quantum teleportation raises deep philosophical questions. What is information? In a classical world, information can be copied infinitely. But quantum information is unique. It can only be moved, not copied. This fundamentally changes our understanding of information. Locality of reality. Quantum entanglement shows that the world isn't completely local. Actions in one place instantly affect distant objects. Of course, this doesn't allow transmitting information faster than light, but it still forces us to reconsider our notions of space. Nature of causality. If measuring particle A affects particle B instantly, but we can't use this to transmit information, what does this say about cause and effect? Physicists are still debating. Identity problem. If we could teleport a human, destroying the original and recreating a copy with the same quantum states, is it the same person? Philosophers call this the teleporter problem, popularized by Star Trek. Okay, let's dive a bit into the mathematics, but without scary formulas in understandable language. Quantum states, what are they? In quantum mechanics, a particle state is described by a wave function. For simplicity, let's take a qubit, a quantum bit that can be in state -0, -1, or in superposition, simultaneously both 0 and 1 with certain probabilities. For example, 0.6-0 plus 0.8-1. This means, if measured, there's a 36% probability 0.6 superscript 2 of getting 0 and 64% probability 0.8 superscript 2 of getting 1. Before measurement, the particle is in both states at once. Entangled pair. An entangled state of 2 particles might look like -00 plus -11 /√2. This is called a Bell state. It means if one particle is in state 0, the second is definitely in 0. If the first is in 1, the second is in 1. But until measured, they're in superposition of both variants simultaneously. What happens during teleportation? Alice has an unknown state, alpha 0 plus beta 1. Alice and Bob have an entangled pair, -00 plus -11 /√2. After Bell measurement, Bob's particle ends up in one of 4 states, which are transformations of the original state. Bob applies one of 4 operations, depending on the 2 bits from Alice, and reconstructs the exact state, alpha 0 plus beta 1. The magic is that Alice doesn't know what alpha and beta equal. She can't measure them. This would destroy the state. But teleportation works for any alpha and beta. quantum teleportation isn't an isolated technology. It's closely connected with other areas of quantum physics. Quantum computers. Teleportation is used for transferring qubits between different parts of the quantum processor. Quantum error correction. Teleportation allows cleaning qubits from errors without direct measurement, creating quantum logic gates. Some operations are easier to implement through teleportation. Quantum cryptography, QKD. Although quantum key distribution doesn't use teleportation directly, they use the same principles. Impossibility of cloning quantum states. Entanglement for creating correlated keys. Detecting eavesdropping through quantum state disruption. Quantum simulators. Teleportation allows initializing complex quantum states in the simulator, reading simulation results without destroying the entire system, connecting multiple simulators into a single network. Quantum metrology. Entangled states and teleportation help create measuring instruments whose accuracy exceeds the classical limit, the so-called shot noise. Despite progress, many challenges remain. Temperature. Most systems require cryogenic cooling to millikelvins above absolute zero. This requires huge refrigeration units consuming kilowatts of energy to cool a single chip. There is progress. Some photon-based systems work at room temperature, but they're less universal. Scalability. Creating one entangled pair is relatively simple. Creating millions of stable pairs simultaneously is a completely different matter. Quantum systems currently number hundreds of qubits, but practical tasks require millions. Cost. One quantum computer costs tens of millions of dollars. Creating a quantum network between cities, hundreds of millions. Satellites like Mischius, programs costing billions of dollars. Standardization. There are no unified standards for quantum communications yet. Different laboratories use different protocols, different types of qubits, photons, ion superconductors, diamonds with defects. A real quantum network needs compatibility. Infrastructure. Regular fiber optic absorbs photons. You need to either lay special fiber, build a network of ground stations, or launch satellites. All of this is expensive and complex. It's no surprise that quantum technologies attract attention from military and intelligence agencies. Secure communication. The main interest is absolutely secure communication between command centers, submarines, aircraft. China has already deployed a quantum-protected communication line between Beijing and Shanghai, 2,000 kilometers long. The USA, Europe, Russia, India, all are working on military quantum communications. Quantum radars. Using entangled photons, you can create a radar that's harder to fool with interference. It can also detect objects with lower reflection. The quantum computer problem. Paradoxically, the development of quantum computers is a threat to security. A sufficiently powerful quantum computer will be able to break modern encryption, RSA, elliptic curves, which protects everything from bank transactions to state secrets. Therefore, post-quantum cryptography is already being developed, encryption resistant to quantum attacks. And quantum teleportation with quantum key distribution are becoming an alternative, physically protected communication. Quantum technology race. Essentially, there's a new technological race, like the space or nuclear race once was. The country that first creates a scalable quantum computer and quantum network will gain enormous advantage. China leads in quantum communications. The USA, in quantum computers. Europe is actively investing in quantum technologies through the Quantum Flagship Program with a budget of 1 billion euros. Not only the military are interested in quantum technologies, business is also investing. Financial sector, banks and exchanges are interested in secure transaction transmission, ultra-precise time synchronization, critical for high-frequency trading, quantum algorithms for portfolio optimization. JP Morgan, Goldman Sachs, Barclays are already experimenting with quantum technologies. Pharmaceuticals and medicine. Quantum computers connected through quantum networks can simulate molecules and chemical reactions, accelerating drug development. Quantum teleportation allows distributing computations between different quantum processors. Telecommunications. Companies like AT&T, Verizon, China Telecom invest in quantum communications. They want to offer quantum-protected communication as a premium service for corporations and governments. Tech giants. Google, IBM, Microsoft, Amazon, Alibaba all have quantum programs. They're developing quantum computers and cloud services for quantum computing. Quantum teleportation is a key technology for scaling. Startups. Dozens of startups have emerged. ID Quantique, quantum cryptography, Rigetti, IonQ, quantum computers, PsiQuantum, photonic quantum systems. Venture investments in quantum technologies have exceeded billions of dollars. Like any powerful technology, quantum teleportation raises ethical questions. Access inequality. Quantum technologies are expensive. Only wealthy countries and corporations can afford them. Will there be a quantum divide between those who have access to quantum-protected communications and quantum computing and those who don't? Privacy. On one hand, quantum cryptography protects against eavesdropping. On the other, sufficiently powerful quantum computers will be able to break current encryption. There's a danger that intelligence agencies are already collecting encrypted data, planning to decrypt it in the future with quantum computers. Dual use. Technologies developed for peaceful purposes, medicine, communication, can be used for military purposes. How to regulate the development and distribution of quantum technologies. Environmental footprint. Quantum systems require enormous amounts of energy for cooling and maintenance. When scaled up, this could become an environmental problem. More energy-efficient approaches are needed. Education. Quantum mechanics is complex. We need specialists who understand quantum physics, computer science, and engineering. Educational systems aren't keeping up with technological development. There's a shortage of quantum specialists. Let's dream about the future based on current trends. Next 5 years, 2025 to 2030. First commercial quantum networks between major cities in China, USA, Europe. Quantum-protected communication becomes available to corporations and governments. Quantum computers reach hundreds of thousands of qubits, begin solving practical problems. Standardization of quantum communication protocols. 10 to 15 years, 2030 to 2040. Global quantum network connecting continents through satellites. Quantum repeaters become reliable and widespread. Quantum sensors in medicine. Navigation, geological exploration. Quantum classical hybrid systems in everyday use. 20 to 30 years, 2040 to 2055. Quantum internet as standard for critical infrastructure. Distributed quantum computing. Quantum supercomputers from connected nodes worldwide. Quantum technologies in consumer devices? Debatable. Might be too expensive. New applications we can't yet foresee. What's unlikely? Teleportation of macroscopic objects. Remember, need to scan 10 superscript 2 atoms. Human teleportation, technically and ethically problematic. Faster than light communication, fundamentally impossible. Quantum smartphones in your pocket, decoherence and temperature requirements. Quantum teleportation isn't the only way to solve quantum communication tasks. Quantum key distribution, QKD, without teleportation. Protocols like BB84 don't use teleportation, but also provide secure communication through quantum channels. They're simpler to implement, but less universal. Post-quantum cryptography. Mathematical algorithms resistant to quantum attacks. Don't require quantum equipment. Work on regular computers. But theoretically can be broken. We just don't know how yet. Classical quantum networks without teleportation. You can transmit qubits directly, e.g., photons through fiber optic, without using entanglement and teleportation. But distance is limited due to losses. Quantum memory. Instead of teleportation, you can store quantum states in quantum memory and physically transport it. It's like a flash drive for qubits. But quantum memory currently stores state for seconds or minutes, no more. Each approach has pros and cons. Future systems will likely combine different methods, depending on the task. Let's debunk the most common myths about quantum teleportation. Myth 1. Information is transmitted faster than light. No. To complete teleportation, you need to transmit 2 classical bits from Alice to Bob. This transmission is limited by the speed of light. Yes, entanglement is instantaneous, but without classical information, Bob can't reconstruct the state. Myth 2. You can clone quantum states. No, the no cloning theorem is a fundamental law. Teleportation moves the state, destroying the original, but doesn't copy it. Myth 3. It's all theory, doesn't work in practice. No, quantum teleportation is a routine procedure in many laboratories. Thousands of experiments have been conducted, satellites launched, networks being built. Myth 4. Soon we'll teleport like in Star Trek. Alas, no. Teleportation of macroscopic objects runs into fundamental problems. You need to scan and transmit information about an incredible number of particles. This requires technologies we won't have for decades, if ever. Myth 5. Quantum mechanics is mystical and doesn't obey physics laws. No, quantum mechanics is the most precise physical theory, tested by millions of experiments. It's strange from the perspective of everyday intuition, but mathematically rigorous and predictable. Myth 6. Entanglement enables telepathy or mystical connection. No, entanglement is a physical phenomenon unrelated to consciousness or telepathy. You can't use it to read minds or transmit information without a classical channel. Let's look at several real experiments that changed everything. Innsbruck, 1997, first teleportation. Anton Zeelinger's team used entangled photons and parametric light conversion. The distance was tiny, several meters on an optical table. Success rate, about 25%. But it worked. For the first time in history, a quantum state was teleported. Zeilinger later recalled, "We weren't sure until the last moment. When we saw the results confirming teleportation, it was incredible. We proved that the 1993 idea works in reality." Calgary, 2016, City Network. This was the first experiment in real urban infrastructure not in an isolated laboratory. Existing fiber optic under city streets was used. Photons passed through a noisy environment. Power lines nearby, cars driving, street lights shining. Teleportation worked. This proved. The technology is ready to leave the laboratory for the real world. Mishi's satellite, 2017 distance record. The Chinese satellite at 500 kilometers altitude teleported photons to ground stations in Tibet. Photons pass through the atmosphere with its turbulence, humidity, clouds. The key to success: space vacuum. Photons traveled most of the way without absorption. This showed, for global quantum networks, satellites are needed. Ground lines have limitations. You might ask, okay, this is all interesting, but how will it affect MY life in the next 5 to 10 years? Directly, almost not at all. Quantum technologies will be in data centers, military systems, scientific laboratories. You won't see them. Indirectly, more secure banking transactions. Banks will start using quantum protection. New drugs developed with quantum simulations. More accurate weather forecasts, quantum computers. Better navigation, quantum sensors. Long-term, quantum technologies could change the world just as computers and the internet changed it over the past 50 years. The first computers occupied entire rooms and were only accessible to universities. Now everyone has a smartphone more powerful than those supercomputers. Maybe in 30 to 40 years, quantum technologies will become just as commonplace. But that doesn't mean you'll have a quantum teleport at home. If this topic interested you and you want to learn more, for beginners, popular science books by Brian Greene, Sean Carroll, Leonard Susskind. YouTube channels, Veritasium, PBS Spacetime, Minute Physics. Anthropic's website has great explanations of quantum concepts. For those who want deeper, textbooks, Nielsen and Chuang, Quantum Computation and Quantum Information. Online courses, mit Open Kurseware, Coursera Quantum Courses. Scientific articles on arcs4.org in the QuantPH section. For keeping up with news, phys.org, Quantum Magazine, Science Daily. Scientific journals, Nature, Science, Physical Review letters. Company blogs, IBM Research, Google AI, Microsoft Quantum. So, what have we learned about quantum teleportation? It's not fiction. It's real, working technology based on fundamental laws of quantum mechanics. It's not magic. It's mathematics, physics, and incredibly complex engineering. Teleportation doesn't violate nature's laws, but uses them in the most elegant way. It's not about teleporters from movies, but what actually happens is perhaps even more interesting. We've learned to transmit information in a way that seemed impossible, using fundamental properties of reality. It's only the beginning. Quantum teleportation opens the path to technologies that seemed like science fiction. Absolutely secure communication. Quantum computers solving problems inaccessible to regular computers. Ultra-precise measurements. Quantum mechanics shows us that the universe is much stranger and more amazing than we thought. And this isn't a reason for concern, it's a reason for admiration. Every time scientists successfully teleport a quantum state, they're not just performing a technical trick. They're proving that reality is fundamentally non-local, that information in the quantum world behaves completely differently, that nature permits things that seem impossible. We live in an amazing time. A quantum revolution is happening before our eyes. The first quantum technologies are already working. The next 20 to 30 years will show how far we can go. Be curious. Follow science news. Quantum physics isn't something distant and incomprehensible. It's the study of the nature of reality, and the results affect all of us. Be critical. Don't believe headlines about quantum breakthroughs that promise the impossible. Real science is amazing by itself, without exaggeration. Be inspired. If you're young and choosing a profession, quantum technologies offer incredible opportunities. Physicists, engineers, programmers, mathematicians, all are needed in this new field. Quantum teleportation teaches us an important lesson. What seems impossible today can become reality tomorrow. The boundaries of the possible are constantly expanding. And who knows what other wonders quantum physics will reveal to us. Thanks for reading to the end. I hope you learned something new about quantum teleportation and how strange and amazing our world can be at the quantum level. If this was helpful, subscribe, and definitely write in the comments. What other topics from quantum physics interest you? Quantum computers? Schrodinger's paradox? Quantum cryptography? Until then, stay curious, friends. And remember, the reality of the quantum world is far more interesting than any fiction. See you in the next video.